Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lecture of module 5, that is on TIG or plasma based wire arc additive manufacturing. So in this lecture today we shall discuss about the introduction to TIG based wire arc additive manufacturing, where the deposition process will be discussed based on TIG, and also deposition process based on plasma will be discussed. Then briefly the process cycle, that is as similar as it is for the MIG based WAAM. Again the process parameter, those are also very much similar with the MIG based WAAM. And then the geometric modeling. However, the geometric modeling is also very much similar with MIG based WAAM, but here another very interesting phenomenon is to be considered, that is the melting position of the wire into the arc. Then the defects are also very much similar as we discussed for MIG WAAM, but the additional new type of defect will come into picture, that will be called as omnidirectionality. And then we shall discuss the different types of TIG WAAM processes based on like 3-axis, 5-axis, serial kinematics, parallel kinematics and hybrid kinematics based systems. So this gives the classification of the wire based additive manufacturing, and particularly today we are going to discuss about the metal wires. Those can deposit the material continuously on the substrate. It can use either serial kinematics, parallel kinematics or hybrid kinematics on the machine tool. And the energy source will be arc, that is our focus. And in arc as well, particularly we are going to discuss about TIG or plasma based heat source. Then we shall discuss the method of generating no support and the multi-axis kinematics, where we can tilt the component and build the part to eliminate the need for support mechanism. So tungsten inert gas, or popularly known as gas tungsten arc welding GTAW, utilizes a non-consumable electrode to create arc, and in that arc we feed a wire from the side, and that arc creates a molten pool, and in that molten pool we feed a wire. So a typical tungsten inert gas welding setup is shown here in this figure. It consisted of a welding torch, at the center of which there is a tungsten electrode. This is the tungsten electrode. The non-consumable tungsten electrode creates arc. This is the arc. And it creates a molten pool onto the substrate. So this is the molten pool. And in that molten pool, a wire is fed from side or from different mechanism. Also, an inert gas is supplied into the welding zone through an annular shape path surrounding the tungsten. So this is the tungsten, and surrounding it there is an annular path from which the inert gas used to come. And this inert gas effectively displaces the atmosphere around the molten pool, and hence it avoids the oxidization of the immediately or the hot melted material deposited on the substrate. A filler wire, which is shown here, is fed towards the molten pool, which after getting melted deposit the material onto the substrate or pre-built layer. It can be noted that unlike MIG WAAM, there is a separate control over feeding the wire. We have seen that in the MIG welding based additive manufacturing systems, usually the machines are having a synergy between the wire feed rate and the current. If you increase the current, automatically the wire feed rate can increase. However, in the case of TIG based systems, we can increase the current separately for the arc, and the wire feed rate is controlled separately by the user. So due to the non-consumable electrode used in the case of TIG based WAAM, the preferable thing is to generate more energy onto the substrate, not onto the tungsten electrode, because we should not consume that tungsten electrode by generating more energy. Therefore, usually the direct current electrode negative is preferred in this case. DCEN is preferred, so that 70% of heat can be generated on the substrate. Also, if not DC, then AC is preferred, so that 50-50% energy can be generated on both the sides. The AC current is usually required to reverse the polarity in cycles to deposit the materials such as aluminium. We have already discussed the similar way it was used in the case of MIG welding as well, because when we deposit aluminium, immediately it got oxide, and this oxide is usually having a very high melting point and it is difficult to break further. To break that oxide, we reverse the polarity and then electron passes from the substrate towards the electrode, and as a result these oxide layers are break. So in half circle oxide layer break, and in half circle the material is deposited. So in AC polarity we can deposit the material in the case of while dealing with the aluminium like materials. Also, more often a step pulse DC current is also used instead of just steady DC, where the current level is maintained at two levels as shown in this figure. The low level is called as background current and the high level is called as peak or welding current. The low level is used for cooling the deposited material, and this high level of current or the peak current is used when the material is actually deposited. In this way, we can maintain an average current or the average power, as the current is directly proportional to power, very much stable, very much low, and as a result heat input will be quite low. So I'll show you a small video of the TIG welding process. This is the arc generated, and you can see now in this arc the wire will be fed. It can be noticed that when the arc is illuminating, that means it is giving the peak power or the peak current is given to it, and that time only the wire is getting melted. Remaining portion of the arc, which is at light color here, is corresponding to the background current, meaning to say at that time only arc is maintained but deposition doesn't happen. Also, the plasma is very much similar to the TIG welding. So in the case of plasma also, a non-consumable tungsten electrode is used to produce arc. However, in the TIG welding process, an inert gas is used just to protect the environment or just to protect the molten pool from the atmosphere. While here in the case of plasma, the inert gas is not only used for shielding the molten pool, but it is used for two purposes. And it also divided into two portions from the nozzle. So this is the typical architecture of a plasma nozzle. Now there are two gases. One is coming through this annular shape nozzle and another is coming from this annular shape nozzle. In this annular shape nozzle which is inside, there is a tungsten also inside, which is up to a certain height. It is not projected outward. It creates definitely arc, right? And the gases, those are coming from the inner core. This is the inner core here. This is the inner core. These gases got ionized and established the arc further, as you are seeing here, and that is also called as plasma. However, the inert gas, those are passing through the outer periphery or the outer cone, those are just for shielding purpose. So plasma is actually more popular in WAAM as compared to TIG, because there is no protruded or the projected tungsten outside the nozzle. Just the plasma gases are coming, and those are having no issues of hitting the wire to the tungsten. Therefore, the plasma is more popularly used in WAAM. There are few more reasons apart from just only that the tungsten is projected outward, but this I found is the major reason where the plasma is used in WAAM. So as the working principle is quite similar in the case of plasma and TIG, they both uses the non-consumable electrode, their process parameters and other related things are quite similar, and as a result we are going to use these terms interchangeably in our further discussions. So this is a typical TIG based system you are seeing here. This is the tungsten. It is creating an arc, and that arc is creating a molten pool at the bottom, and in that molten pool a wire is fed. A similar system is shown here again, where this is the TIG nozzle or the TIG torch, and there is a tungsten here projected and it creates arc, and in that molten pool we feed the wire. When the system is mounted on a robotic arm, it looks something like this. So this is the robotic arm shown in yellow color here, and this is the plasma torch, not the TIG torch. Please note that, because there is no protruded tungsten outside. And in this plasma, we are going to now feed the wire. What you are seeing here right now is the pilot arc. It is not the main arc, because main arc will be generated when the plasma will be passed through and the circuit will be completed between the substrate and the torch. So now the process parameters. So these are the various process parameters for the TIG WAAM. First is of course the power. Power is governed by the arc voltage, starting, main, reduced and final current. That is why P into V. So we know that power is equals to nothing but voltage into current. So these are the two main parameters corresponding to that the power is decided. The filler wire, wire type such as the material composition, coating, coring, etc., wire diameter and wire feed rate. Please note that I have already mentioned this, that in the case of TIG or plasma based WAAM, the wire feed rate is separated from the current. They are not in synergy. You can separately control the wire feed rate and the current here. The next important category of the process parameter is the gas related parameters, such as the gas proportion, gas pressure, gas flow rate, gas pre-flow period and gas post-flow period. Then the deposition related parameters such as the layer height, bead width, bead height or reinforcement height. The bead height is also called as the reinforcement height. The torch related parameters such as the distance between the nozzle and the base, that is also called as the standoff distance, distance between electrode tip and the base plate, that basically going to give you the arc length, and then the torch speed. The path related parameters such as which type of area filling path you are using, what is going to be the step over between the two consecutive passes and the machining allowances if required. So very much similar to the MIG WAAM, here also to start with the process we used to perform 3 experiments. First corresponding to the single bead experiment, the second is the multi-bead experiment, third is the multi-layer experiment. So this is an example of single bead experiment, this is multi-bead experiment and multi-layer experiment, and finally we get the component after getting the optimized parameter corresponding to these three experiments. So let us first discuss about the geometric modeling of the deposited material. We know that for the single bead, as we deposit the material, we need to assume some cross-section profile of the deposited bead and try to find out the correlation with the process parameters. Here it is going to be very much similar as we discussed in the case of MIG WAAM. So single bead experiment, multi-bead experiment corresponding to XY plane where we used to find out the optimal step over, that also going to be very much same here. Also the multi-bead Z plane deposition, I mean the bead one over another, this type of deposition. So what will be the height of the thin valve if you are depositing after depositing 10 layers or something like that. So that can be obtained with a similar fashion, with a similar way which we did for MIG welding also. We did for MIG welding. However, there is one interesting and very important phenomena corresponding to the geometric modeling, that is the melting position or droplet landing position. Let us observe this one. The wire is coming from side and the tungsten is creating an arc. As the wire goes into the arc, it absorbs some of the energy, and now it is very much likely possible that where the wire is going to melt, it may not hit the molten pool at all, and instead the wire may get melted at a certain location which is way before the molten material is getting formed. So in that case, from that height the material will be transferred into the droplet forms, and that should be called as droplet transfer of the material. It may be also possible that the wire is coming up to a certain height and then after that it is getting melted and creating a droplet, and that droplet is just connected with the molten pool, and hence a bridge transformation is happening. Bridge transformation means the bridge between the molten material and the wire is liquid material only, and that is called as bridge transfer. This is the most optimal condition of melting the wire into the TIG welding. But now if I further increase my speed of the wire, in that case wire may not get melted and it may directly hit the molten pool. And as the wire is not getting melted and it is hitting the molten pool or the substrate, in that case there may be a bend in the wire and this may not be desirable for us. However, the first case is also not desirable because it may happen, you may end up landing the droplets offset from the axis where you want to deposit the material. Like an example, some errors corresponding to that are shown in this diagram. So here if you see, there is an offset in the deposition material. It is not exactly melting at the axis of the tungsten or at the center. It is melting slightly before that. In that case, if it is melting at some distance, maybe of 1.5 mm, then you see that our tungsten was here, but it is depositing material from this point onwards. This gap may increase further if the offset between the tungsten axis and the wire deposition or the droplet landing position is changing. So it highly depends on what angle you are feeding the wire and at what speed you are feeding the wire. So these few geometric parameters highly influence the wire feed rate, and it is becoming very much essential also if you are going to deal with very precise deposition by utilizing this technique. We have to identify that where these droplets are going to melt and form the bead to further study. So for that, there was a model developed in 2017 and you can refer to this journal for that, but I'll try to summarize this here and try to obtain a generalized formulation for the same. So as I have already mentioned, it is important to find out the droplet landing position in TIG WAAM in order to have a more accurate system. Therefore, a model will be shown with the following assumption here in this study today. So assumptions are the tip of the wire will be in weld pool after molten droplet formation. Hence, the tip of wire is assumed to be adiabatic. So if this is the tip of the wire, assume that there is a wire very long on the back. So this tip of the wire is going to be adiabatic and no heat will be transferred from this particular area. Heat will be transferred only from this region. That is the outer periphery of the cylinder, not the tip. The shape of the arc is assumed to be Gaussian. Distribution in each slice is also Gaussian, but shape of the arc, this bell shape, is also assumed to be Gaussian. Further, inside that, if I take any cross section at a particular height, for example, if I take a cross section at this particular height, I will obtain, let me draw this top view, I will obtain the arc cross section something like this, and the intensity inside this is also varying by Gaussian. So there are two things now. The shape of the arc is also assumed to be Gaussian, and also at each height, if I take the cross section, the intensity of the arc inside that is also varying by the Gaussian profile. Again, the next assumption is the height of the tip of the arc is the same as the arc length. So this is the arc length and this is going to be assumed as the height of the tip of the arc. The arc column boundary is positioned where 90% of the maximum heat flux occur. So as we have assumed this profile to be Gaussian, we assume that its radius is where 90% of its height is going to be reduced. So if this height is L, we will find the position of H where H is equals to 0.05 times of L. Next is the drop falls vertically at the same location where the tip of wire melts. The another assumption is the drop if they melt at any location, assume that the wire is getting melted at this location, they then after that are not following the same trajectory, they are just falling vertically from that point and then depositing the material. So with these assumptions, let us try to develop a model. So the first one is, assume that the boundary of the arc is a Gaussian curve. So what you are seeing here, this curve is representing the boundary of the arc, and if this is the boundary of the arc, we are going to assume it to be Gaussian profile. Hence the height at any point, if I take height of this curve, will be given as L exponential minus k r square, meaning to say, if the r is 0, r is nothing but the distance from the center to the boundary point. So anywhere from this point to this point is the distance r. So if this r is 0, you can see that is nothing but the point at the tip, and that will be the height of the arc, and that is going to be equal to the L. So h will be L at r equals to 0, and you can see also from this diagram. Now how do I find out this constant k? We have already said r is the arc boundary radius at 90% of maximum heat flux. As the heat flux and the boundary shape both are Gaussian profile, then I can say wherever the value of Ri is equals to R, I am interested in this. So wherever this is radius is equals to capital R, and in that case the height of the boundary or the height of the arc has been reduced by 95% of it. Hence it is 0.05 of the maximum height, that is L, right? So in that case it will be 0.005 L, and if I just put Ri equals to R in this expression, I will get this. As a result, your value of k will be equals to 3 by r square, and we have got that constant, and we can put it in this equation. So this equation, what you are seeing here, is going to represent the boundary of the arc, right? So by utilizing this equation, if I want to find out what will be the radius of the arc at this height, you can just put the value of h in that case here, and you can obtain the value of Ri, right? So for example, if I am interested at this hi, so this is hi, I'll just extend it up to this point. This radius from here to here, okay, this one will be nothing but capital Ri. Also, this wire assumed to be entered, assume that the wire is getting entered into the arc at this particular point, that is represented by R naught H naught, and it is going in a straight line. Now how can we find out the equation of this straight line? Assume that the wire is entering at this location and it is at an angle theta. So the equation of a line which is entering at an angle theta can be given as y equals to, as this angle is measured in clockwise manner, this will be minus tan theta x plus h y h, because at x equals to 0 at this location, because if I put x equals to 0, the wire is coming at this location at the tip, and it is meeting with the axis of the electrode or the tungsten at a height h. So that is why h here. Okay, so this is the equation going to be for my wire entering into the arc. The two things I need to know, only the angle at which the wire is entering and also the offset or the distance from the substrate at which it is meeting with the center line or the axis of the electrode or the center line of the arc. So as I now know the equation of my line along which my wire is entering into, and given by y equals to minus tan theta x plus h, I can easily find out the relation between h naught and r naught. H naught will be nothing but the height of the point at which it is entering into the wire is entering into the arc, and r naught is nothing but the distance of that point from the center line, and that is given here by r naught. Now if this is R naught and H naught, I can put it into this equation, and as a result I will have H naught equals to minus tan theta R naught plus H. Also at this location I want to find out the radius of this, right? I want to find out the radius of the arc, and it is very much same as R naught itself. This is because this is the entry point and they both are same on the outer boundary of the arc as well as the point on the wire, right? They are common here. Rest of the point on the wire may not be on the boundary of the arc, but this point is on the boundary of the arc. That is why R naught, the small r naught, is equal to capital R naught. Fine. So in that case I can use my equation of the arc boundary, which says that H equals to L exponential minus 3 Ri square divided by R square. So Ri is R naught, that is this radius, and H naught is this height H naught, and as a result I can get it from here. So these equation will be used, but I am just in the beginning are noting down this equation corresponding to my equation of the arc boundary. So if the wire is moving in a straight line, right, with the velocity of Vw, that is the velocity of it, the entry point is P naught. If the wire is moving in a straight line with the velocity Vw and the entry point is P naught, then we can easily find out the coordinates of the wire at which it is going to be melted. So assume that after time t the wire is getting melted and it is melting at this particular portion. So the tip of the wire is getting melted at this particular location. So how we are defining this location? I am saying it is at RT from the center, that is the distance from the center along the x axis, right, and it is at HT from the substrate in the y direction, and that is why the coordinate of this point where the wire is or the tip is getting melted is given by PT RT comma HT. I can easily find out the position of this tip because I know the velocity of wire. Hence I know if this is the velocity of the wire in this vector along this vector, what will be the velocity of wire along this vector and along this vector, because I know this angle theta. Hence the velocity along the x axis will be Vw cos theta and velocity along the y axis will be Vw sin theta. If the wire is getting melted at this location, at this RT location after time t, then I can find out the length as well, and the length corresponding to x axis from here to here. If you see here, from this point to the entry point, this distance will be cos theta v naught t, where cos theta v naught is the velocity in this direction and t is the time. Hence this will give you the distance travelled by the tip along the x axis after time t. In a similar fashion, you can find out the distance travelled by the tip along the y axis after time t, and that will be sin theta Vw t. Hence the coordinate of this tip where it is getting melted, RT and HT, can be given as RT equals to R naught. R naught is the x axis position of the wire where it is entering into the arc, R naught plus cos theta Vw t, and in a similar fashion HT, this height will be HT will be equals to H naught minus sin theta Vw t. So it can be also noticed that this is my origin 0, 0, right, and in that case my left side measurement will be in negative, hence this R naught is going to be negative, and that is why I am writing a plus sign here, because this is already negative and we are increasing this negative coordinate by this value. And in the case of H, I am reducing, I am using minus term. It is because I am measuring, this is my 0, 0, and all my measurements in this direction will be positive, and as the wire is coming down, this much distance is going to be reduced from it, and that is why this sign convection is used. Now what will be the radius of the arc at which the wire is melting? So wire is getting melted at this location, right? Now our objective is at this location what will be the arc's profile. So the cross section of the arc, if you take, this is the cross section, right? This is the cross section of the arc at this location, and in that case the radius of arc that is defined by capital RT can be easily obtained by the boundary curve of the arc, and we know that the boundary curve of arc is nothing but HRI equals to L exponential minus 3 Ri square divided by R square. So if I replace Ri by RT in this equation and then further solve, I will be able to get RT square equals to minus R square by 3 ln HT by L, where HT is already known to me, and this is my HT and it is already known to me from this equation. So as we have seen, the wire may get melted at anywhere when entering into the arc, and at different position the profile of the intensity distribution will be different. As I am showing here, this is the Gaussian profile at this particular location, this is the Gaussian profile heat distribution or the intensity distribution at this particular location, and this is the Gaussian profile of the intensity distribution at this location. So in general, if I say there is a point at a distance Ri from here and at a height Hi from the bottom, and this is the location of this point, at that location the expression corresponding to the intensity distribution will be given by this formula. It is not having any H term here. If you notice, it is I, the intensity at this location I, Ri equals to I max exponential minus K Ri square. So what I want to emphasize here, that this expression is independent of Hi. There is no Hi here, right? It is because at any height from the bottom, at any height, if I take this cross section or this cross section, the intensity distribution will be Gaussian and will be dependent only on the distance from the center of the arc. Therefore, this is the equation for representing the intensity distribution at any cross section. So if I take a cross section at a height Hi and I want to measure the intensity at a particular distance Ri from the center, then this equation will be useful. So I am writing this expression here again. It says I at a distance Ri will be equals to I max exponential minus K Ri square. Now our objective will be to find out again this constant K, and this constant we have already find out for the intensity distribution in a Gaussian profile in the case of laser. But let us do it again. So it says if it is a Gaussian distribution really inside, then at Ri equals to some R, capital Ri, that is nothing but the boundary of this curve which is represented by Gaussian again, this position will be obtained when the intensity will be reduced by 95% of its maximum intensity, and maximum intensity is how much? That is 0.05, and hence when it will become this much of the maximum, that will be the position Ri, and that will be nothing but the boundary everywhere. So in that case, let me put this value as I max exponential minus K Ri square. When the I max will get cancelled, and we can easily obtain from here the value of this coefficient K, and K will be equals to 3 by Ri square. As a result, your expression for intensity will be I Ri equals to I max exponential 3 small Ri square divided by capital Ri square, where the small Ri square is nothing but the distance from the center of axis to anywhere into the arc, where capital Ri is the distance from the center of the axis to the boundary, okay, to the boundary of the arc. Now our aim will be also to find out this I max, what will be this maximum intensity. This also can be done easily. Let me take any arbitrary cross section from the arc, and the intensity distribution into that corresponding cross section can be given by this expression. Now let us try to find out the total power inside this. And how can we do that? Assume that this is the cross section of the arc at a particular height. Then intensity is varying maximum at this center and towards the boundary, and boundary is where 90% of its energy get lost. So I am assuming a strip at a distance Ri of thickness Dri, and let me get the power in that case. So the power into this strip will be equals to, the power will be equals to 2 pi Ri, that is the area of it, into d Ri, that is the thickness of it, right. 2 pi Ri, that is the periphery of it, and dri is the thickness. So multiplying these two will, I'll get the area, and if I multiply this area with the intensity distribution, and hence I will get the power into the strip. So this is the power into this tiny strip. If I integrate it from 0 to infinity, from everywhere 0 to a very long distance, I will get the total power. And this total power in the case of TIG welding can be given by multiplying by voltage into current, and if there is a given efficiency of the system, multiplied with that also. So eta Vi will be the total power, that will be equals to integration 0 to infinity, and let me replace the expression of IR also from this equation, and as a result I will have integration 0 to infinity I max exponential minus 3 Ri square divided by Ri square into 2 pi Ri dr. Let me integrate it, and as a result I will get this expression, and from here I can easily now find out I max. I max will be equals to 3 eta Vi divided by pi Ri square. Now let me just replace this I max value in this expression here, and as a result my final equation corresponding to the intensity distribution at a particular height into the arc created by the TIG welding will be given as IRI equals to 3 eta Vi divided by pi Ri square exponential minus 3 Ri square divided by capital Ri square. So now let us consider a wire tip micro element length to be dl. So this is the wire, and I am considering a micro tip element length. Assume that this is this much and it is of length dl. Now this dl will receive energy from the top. We have already assumed that the tip of this wire is adiabatic, so no energy will transfer from this, but from the surface of it energy can enter into it. So let me make it little bit larger also. This distance is dl and this wire is coming at an angle theta, we know that, right. In that case the surface area at from which the energy can enter into it will be nothing but the projected area. So it can be easily calculated, because we know that this distance from here to here, it is 2 Rw, twice of the radius of the wire. So the projected area will be 2 Rw into dl, that is the area of this rectangle what you are seeing here, into cos theta. If I multiply it by cos theta, I will get the projected area, right. And that area, only that much area is going to receive the energy into the arc, right, and it will be given by 2 Rw cos theta dl. Now the energy required to melt the tip of the wire can be given by this particular equation. It says Cp, this is mass and this is the temperature difference. So as the wire is entering into the arc, its tip, I am just considering only this much area, okay, this much length only, that is dl, and if the cross section is pi Rw square, that is the cross section of the wire, and if the length is dl, so they both get multiplied, pi r square dl will be nothing but the volume of the wire which we are considering here. And if I multiply it by density rho, that will give me the mass, and as a result Qm will be equals to Cp rho pi Rw square dl bracket Tm minus T naught. So this much energy is required to melt this tip of the wire of dl length. So this tiny tip what you are seeing here required this much energy. Now this is fine, but how much energy is available for this tip when it is traveling inside the arc? For example, you have the tip here and it is keep on traveling inside it. It's a very tiny small element we are considering. So after what time this much energy it will get absorbed when it will travel into it? It can be also easily calculated. We know the intensity, right, by this formula. So we can find out this intensity into the area from where it is absorbing the energy. We have already seen that. That will be 2RW cos theta dl. And assume that if the whole thing is traveling into the arc after time t, the energy absorbed by this will be given as Q equals to integration 0 to t, this expression of I into the area of the projected area of the element. So let me write it as dA into the time dt. In dt time, wherever it will reach, that time, a small amount of time dt, and integrated from 0 to t. So from 0 when it is entering into it to the time t when it is reaching to this element is reaching up to a certain position, the energy absorbed by it can be given as Q. Now if you want to know whether it will get melted or not at this location or after time t, these two energies should be equal. The energy required by the wire tip to get melted, that is Qm, should be equals to the energy absorbed by the small element when it is traveling inside the arc, and that is given as by Q. So in that case, you have to consider and write a program maybe in MATLAB or another language so that you can simulate it and get your final result. So how it will work? Start with entering the value of the input parameters such as the melting point of the wire, the rho, the density of the wire, the velocity of the wire. So all these parameters you need to enter in the beginning. Then first calculate the value of Qm required to melt the tip of the wire. Assume any value of dl, anyway that is not going to affect, but assume any value of the dl and then find out the how much energy will be required to melt this tip. We have already seen that it was given as Qm equals to mCp delta T, where m is nothing but the mass of the tip, and this is the tip you are seeing here, and the mass is nothing but rho pi Rw square into dl. So this much energy will be required. So let us see when this tip is moving inside the arc, at what time this much energy will get absorbed by the tip. So for that, let us initiate the process. Initially at t equals to 0, zero energy will be absorbed because the element is just outside, right? So no energy will be absorbed. But when the tip is moving inside, so assume that it has moved in a very small time dt and it has reached to this particular location. Calculate the energy absorbed, and this can be done by the formula which we have seen, Q equals to integration 0 to t IR, the projected area ds into dt. So by that equation you can very easily calculate the energy absorbed by the tip of the wire in a small time. Then keep on increasing this time and keep on adding the energy absorbed by the wire at this stage and the next stage. So for example, at this stage, for example, the energy absorbed is 0, but at this location the energy absorbed is Q1, and at this location the energy absorbed is Q2. So total energy absorbed by the wire tip when it is reaching to this particular location will be Q0 plus Q1 plus Q2 and so on, and Q2. So if this much energy is absorbed, let us check now whether this much energy, the Q, is greater than the energy required to melt the tip. If it is greater, then fine. It means it will get melted at that location or before that location. But if it is less, that means further movement of the wire will happen. So by using this workflow, by using this algorithm what you are seeing here, you can easily find out where the wire is going to be melted and land the droplet onto the substrate. So we have already assumed if the wire is getting melted at this location, it will drop the droplets immediately here, vertically downward, and that will be the location of wire melting, or from this position only you will consider that there will be a slight offset in your deposition. If your wire tip is not getting melted anywhere and you are not getting any solution, that means wire is not going to melt into the arc and the wire feed rate you have to reduce, or you have to change some other parameters like the current into the arc, because if you increase the current into the arc, of course your intensity will increase, and as a result your wire may get melted earlier. So it is very important now, if you are dealing with TIG WAAM based process, to identify where your wire is going to get melted. Now let us discuss about the defects in the TIG WAAM process. These defects are like the residual stresses, porosities, and crack or delamination are very much similar like we discussed in the case of MIG WAAM. Here in TIG WAAM also similar types of defects usually occur, and the elimination methods for the same are very much similar like we discussed in the case of MIG WAAM. However, a unique problem occur in the case of TIG WAAM, that is called as omnidirectionality. So what happened? First of all, let me just define what is this omnidirectionality. So the term omnidirectionality indicates an equal sensitivity of the process in all the directions. An omnidirectional antenna, for example, it receives signal from all the sides, right? While a directional antenna can receive signal only from one side. In a very similar analogy, an omnidirectional process in the case of wire arc antenna manufacturing can move in any direction without any issue. But if it is not capable of moving in any direction independently, then the process is not omnidirectional, and some additional auxiliary arrangement has to be made to make the process omnidirectional. So as in the case of TIG WAAM, you know that we feed the wire from one end like you are seeing here. So this is the tungsten creating the arc, and into the arc and into the molten pool created by the arc we are feeding wire from one side. Now assume that the wire is getting fed from side and you are moving on a circular trajectory. So this black color trajectory what you are seeing here is the motion of the tungsten. This is the trajectory corresponding to the tungsten, and your wire is not getting melting exactly at the center of the tungsten. We have already seen that, right? It is slightly melting offset from this, so maybe at this location. And now as you are moving on a circular trajectory, what will happen? You will deposit the material along with the red circle. Hence, when it will become side feeding, front feeding, and then again side feeding, and then again back feeding while moving on the same trajectory. As a result, the geometric and metallurgical property of the fuse layer are not going to remain same at all the locations, and hence the process is not omnidirectional. You can see when we deposit a bead inside a slot and measure its height and width, we have found a very good variation. The process is not omnidirectional and giving lot of variations into the deposited material. Hence, the process has to make the omnidirectional. You can see this video. This is a conventional TIG, and we starting at this position. In the beginning it was side feeding, now it is front feeding, and now again it is becoming side feeding, and then again it has become back feeding, and now again you can see that it has become side feeding. So you are moving on the simple trajectory, but different kind of feeding mechanisms are occurring. The set parameter for a corresponding feeding mechanism, like for example you have optimized your parameter for front feeding of the wire, they may not be optimal when you move in any other direction, and the deposited bead may not give you the same metallurgical or geometrical properties. Therefore, the process has to be omnidirectional, and this is a major issue we usually face in the case of TIG based WAAM. So this diagram shows the bead which is deposited in the green color, the reference slot which we have made, and it is showing the path of the torch also in blue color. So it is obvious from here that the bead is not uniformly distributed on both the sides of the path of the torch, while it is sometimes offsetted on one end and sometimes it is offsetted on another end. And at some portion, yes, it is uniformly distributed, but that may be the optimal wire feeding condition for that particular type of feeding. Also, there is a huge deviation in the width of the deposited bead and its height also. 0 to 360 means here we are measuring the angle from here, this is 0 degree, and then I am going like this and measuring the angle from 0 to 90, 180 and 270. And at different locations, the black color curve shows the height change in the deposited bead and the red color curve shows the change in the width of the deposited bead. The top view of the same molten pool can be seen from here also. So, like I already mentioned, the wire may not melt at the center of the arc, or it may melt at some particular distance, and that distance I am writing here at dm. Due to this offset in melting, so this is the side view of the same molten pool, this is the molten pool. So, instead of melting the wire at point PC, the wire is getting melted at point PM. Now, due to that, when I am moving in on a when I am moving on a non-linear trajectory, as a result I will deposit something like this. Another issue is also, as you assume that there is an arc on the top here and some of the energy of the arc is getting absorbed by the wire and at this portion. As a result, the penetration in the substrate will not be uniform. It will be higher on this side, it will be high on this side, while the penetration in the substrate will be low on this side. So, due to that also you will get a non-symmetric penetration into the substrate. So, how do we resolve these issues related to omnidirectionality in the case of TIG or Plasma-WAAM? So, these are the 4 general methods of eliminating the omnidirectionality. One is either you feed the wire and then along the same vector at which you are feeding the wire, the arc should be generated. But we know that it is not really possible in the case of TIG WAAM because we are generating arc from a different source and feeding wire into it, while it is very much possible case in the case of MIG welding. Another possibility is we keep the arc at the center. So, this is the arc at the center and surrounding it from all the sides we feed the material. Now, in that case, as we are maintaining a uniform distribution of the material fed into the molten pool, there will be a symmetry, and now you can move in any direction, your process will be omnidirectional. Other possibility could be, as your wire is at the center and you generate the arc in a conical form surrounding it, as you are seeing here. In that case, preferably you should have a hollow tungsten electrode type of arrangement. The fourth and the easiest one is dynamically adjusting the feedstock. This is the most common and the most popular method which has been adopted by most of the commercial systems of TIG WAAM. So, here the wire is fed like this, and for example, this is your direction of motion of the torch. Now, if there is any angle maintained theta between the direction of motion and the wire feed, then it should remain constant, then the process will be omnidirectional. Now, to do that, if I am reaching at another location and now I am moving in this direction which is tangential to the point on the curve, now in that case, to maintain the value theta between the vector Vt and Vw, I have to rotate my wire appropriately. So, either we rotate the wire or we rotate the substrate, but this angle has to remain maintained, this theta should be maintained. Now, let us look at how these systems will look like if we implement these methods which I just explained to you about the omnidirectionality. The first one is the coaxial fusion source surrounded by the feedstock. So, the center is the tungsten which is generating the arc and it is creating a molten pool on the bottom. Now, instead of having only one wire, we are going to have 3 wires, and these 3 wires are forming a cone like this. It's an approximate cone, but if you look at the top view of the arc, then you will find it in this manner, where the feedstock is entering into the arc at 3 different angles from 3 different sides, and it is making an approximate similarity around its center. Now you move in any direction, the condition for feeding the material will remain same. However, the better version could be if we could feed these wires in a conical form. But that is very difficult because wires are always available in the cylindrical form, and in the feeding them in a finite cone will be very difficult task. However, it is very much possible if you have powder as a raw material. But unfortunately with TIG we cannot use powder as a raw material. So for wire we have to just approximate the same thing and feed 3 wires from 3 different sides at a 120-degree apart angle. The another possibility of obtaining the omnidirectionality in TIG is by feeding the wire at the center. So this is the wire and it is coming from the center, and there is a hollow electrode, and there is an electrode here which is hollow in nature. So as this is a hollow electrode, definitely you will be able to feed the wire at the center and this arc will be created. Now it is nothing but creating a conical form of arc, right? And in that you are feeding wire from the center. Now you move in any direction. If you look at it from top, you will see something like this. There is an arc generated by the hollow electrode, and at the center of the same you are going to feed the wire like this. Now you move in any direction, the process will be omnidirectional. This has already been filed in a patent which I have mentioned here, the provision of having a tungsten electrode. So it is very much possible. Next very popular method of achieving omnidirectionality in TIG is by dynamically adjusting the feedstock or deposition direction. So as this is the wire you are feeding into the molten pool, right? And as the direction of the deposition is given by this vector and it is keep on changing. For example, it is at that location, that will be tangent to this. Now if the torch will reach here, this will be the direction of deposition. What we want to maintain the angle between the wire feed and the vector Vt, the direction of the torch motion. So to do that, what we can do, we can actually dynamically keep on changing the direction of Vt in such a way that this angle remains maintained. I will show you the same example where the TIG welding torch was used to deposit on a circular geometry. Here now I am going to rotate the substrate in such a way that a particular type of feeding mechanism will remain maintained. So here you can see this is a front feeding, right? And all the time if you observe, it is the front feeding. While in the previous case which we have seen, that when the torch was moving and there was no motion on the rotary axis, the wire was giving front feeding, back feeding and side feeding and all at different locations. But here you have seen that it was always maintained front feeding. The another possibility could be we rotate the wire feeder itself. So the wire feeder in that case will be attached with the bearing on another axis about the axis of the tungsten, and then it will keep on rotating around it accordingly. So this is a CAD model of the same. So here you can see there is a mounting available, and if the motor will rotate, you can see that based on the motion of the torch, the wire feeder is also changing its position and all the time the feeding mechanism is maintained. This will be called as the dynamically adjusting feedstock direction. So most of the TIG based WAAM processes utilizes the dynamically adjusting the feedstock direction. Even if you are using, for example, a robotic arm, the Z axis which is at the tip of the robotic arm is usually utilized to feed the wire accordingly. So that axis, particularly if you are going in that direction, will keep on rotating the wire feeder also appropriately. Now let us discuss about some other methods with TIG based WAAM. So the other systems like where we utilize the 3-axis machine, 5-axis machine, the serial kinematics, the parallel kinematics and the hybrid kinematics on the machine tool side are very much similar to what we discussed for MIG WAAM. Therefore, in this TIG WAAM based system, I am not going to go into the details of it. The same machines can be utilized just by replacing the MIG welding by the TIG welding or plasma. Some of the case studies done by the Plasma wire arc additive manufacturing by WAAM 3D Limited are shown here in these diagrams. So here you can see a very big component was prepared by depositing the material through this technology. So there is a robotic arm here, and on the tip of the robotic arm, if you see this diagram, there is a plasma which is generating the plasma here, and into the molten pool created by the plasma, a wire is fed into. The material here used is the titanium. So this was all about the wire arc additive manufacturing. We have discussed about the MIG based wire arc additive manufacturing, and we have also discussed about the TIG based wire arc additive manufacturing. Now we shall discuss about the wire beam additive manufacturing. So with this, thank you very much.